Okay, I'll start now. Thank you everybody for joining us in the first SNAPP seminar of 2022. I'll hope that everybody had an enjoyable winter break and that we are renewed in energy to start afresh. Today's our first speaker of the year is Ramon van Handel, who's an associate professor at Princeton University. His interests lie broadly in probability theory, analysis, geometry, and their interactions. And he's also an Erlang Prize winner. So with that, Ramon, please.
Thank you, Mariana. Everybody can hear me? We're good? And you can see my screen? All right. Well, thank you for the invitation. So I want to tell you about a bunch of recent results that we have on random matrices. We worked on this for many years, and we're very happy with it. And I think in particular that these results can be tools that are very useful in applications. And I'm going to try to give you some sort of high-level overview of how they work and what you might be able to do. So what is random matrix theory, right? So we're talking about random matrices. So the general goal of random matrix theory, right, is to understand the eigenvalues, let's say the spectrum of a random matrix, right, of random matrices. So I give you a matrix, let's say a D by D random matrix of some sort, right, some model of random matrices, and we would like to understand how their eigenvalues behave. Now, what is a random matrix exactly, right? I haven't specified a distribution of a random matrix. So in classical random matrix theory, what people typically study are very special models of random matrices. Right? So in classical theory, people study very special models. For example, one of the most common ones is if they have IID entries, right? So if I have a matrix, and I just stuff it full of, I make all of the entries independent and identically distributed, a D by D matrix of some IID entries, and now I let the dimension of the matrix go to infinity, we can try to study what happens to the eigenvalues in that limit, right? And this way, if you have such very special models, the problem makes perfect sense. You have a sequence of models of increasing dimension that go to infinity, and you can try to study the exact behavior of this model. And this is a very beautiful field. It's a very mature field in which huge amount of detail is known about what happens. And, you know, I'm a little bit exaggerating, but basically what you can do here is that you can compute the exact asymptotic behavior of more or less anything you want. Of, you know, more or less anything. It's a very specific sequence of models. You know, you ask, you know, about what does the spectrum look like? What do the edges look like? What are the distributions of the individual eigenvalues? What is the joint distribution of the individual eigenvalues, et cetera, et cetera, et cetera. You let dimension go to infinity, you scale properly, you can write down exact formulas for all of the, you know, distributions of these limiting objects, et cetera, et cetera, et cetera. So I didn't say it was easy, but and the formulas are very nice and they have beautiful structure. But the ability to do that hinges on the fact that you have these very regular models of ID. Now, from another perspective, such models are extremely boring, right? I mean, what is a matrix of ID entities? You just take a matrix and you just stuff it full of noise. There's no structure in this matrix at all, right? And in many areas, both of pure mathematics and of applications, one might be interested in much more complicated models of random matrices that have some sort of arbitrary structure, right? You know, they might not have all entries having the same size, right? The entries might have some arbitrary pattern of the variances, for example. The entries might have dependencies, right? The matrix could be sparse. You know, the matrix could be generated from some underlying data that you're looking at, right? And in data science, for example, these type of questions show up a lot. And these type of methods of classical random matrices are matrix theory are basically useless for studying such general models of random matrices. You know, for each special model, you know, you could sit down and develop a special theory for that particular type of model. But if I gave you a general random matrix that has a general kind of structure, you know, these tools would not allow you to do it. So in the opposite extreme, we could try to study random matrices with totally general structure. course, I mean, what does it mean? I'll give an example, many examples later. So now we don't impose some specific model of the structure. Maybe I just give you a D by D matrix. It has some particular pattern of variances and dependencies and all sorts of things, right? And now I would like to say as much as possible about that. Now, this seems like, it seems like, what could you possibly say about such a thing? If I make no model assumptions, how can I say anything specific about the model, right? I mean, that seems impossible. And nonetheless, it is known that you can say some rough things in this case, right? So in classical random matrices, you can say very precise things asymptotically. In the opposite extreme, if you have some sort of matrix that has a general structure, then at least you can say something very crude about, let's say, the size of the spectrum. You can try to compute, for example, what is the spread of the spectrum. I'm going to show you some standard results in this area, so you get an idea about what is crude information, right? So here we can obtain at least crude information. And in principle, you don't hope for more, right? In theory, right? Because if you make very special assumptions, you can, of course, hope to do exact computations. If you don't assume anything, then what can you hope to say? You might just be able to say some very rough things, right? And that seems like a reasonable thing. And the main message of my talk is that there is something in between these two extremes that seems to capture a very large number of matrices you might encounter. But we will see that as we go. So the simplest, so throughout this talk, I want to work with basically the cleanest setting. Because of course, if I tell you I want to study matrices with totally general structure, I have to make some sort of assumptions, right? So the cleanest setting is the following. Let's take X to be a D by D, self-adjoint. So let's say it's real, then it's symmetric. The fact that it's self-adjoint allows us to talk about eigenvalues that are real, right? So that makes the intuition easier, with mean 0 and jointly Gaussian. And throughout this talk, I'm almost exclusively going to talk about this particular model because this is somehow the cleanest way to express a random matrix with totally general structure, right? Even though I've assumed it has mean 0, you should, and that is Gaussian, you should note that these matrices can have almost arbitrary pattern of variances of the entries, right? The entries are not identically distributed. You can take any pattern, like take any picture, take your favorite painting, and divide it into pixels and take the matrix where each entry is, let's say, Gaussian, whose variance is the intensity of the picture in that, in that pixel. Now you have a very structured matrix, right? And jointly Gaussian matrix entries can also have all sorts of very complicated dependencies between the entries. Right? So this already is an extremely general model. And later I will drop this assumption of mean 0, and we will work with an arbitrary mean as well. But for now, let us keep this assumption in place because it's the cleanest thing to do. So I will make various remarks at various points about that, in fact, we can handle much more general situations than this. But the reason I pick this model is because on the one hand, it allows us to take a matrix with, let's say, totally general structure and have very clean statements of results. And secondly, because it turns out that this is actually one of the main settings of it. But I will get back to that later. So we're taking a D by D self-adjoint centered matrix, but with an arbitrary pattern of covariance, right? So arbitrary variances of the entries, arbitrary dependencies of the entries. Now, what can you possibly hope to say about the spectrum of this matrix? I mean, we're making almost no assumptions about the structure of it. So it's a very beautiful result that dates back to the 1980s that allows us at least to say something about how large is the spectrum? What is the spread of the eigenvalue? And this is the so-called non-commutative Kinchin inequality due to Françoise Louste-Picard and Gilles Pizier in the 1980s. And it gives us an inequality that holds in this completely general setting. It says the following. It says that the expected norm of this matrix. So when I say the norm of a matrix, I mean the largest singular value or the largest eigenvalue in the case of self-adjoint matrices, or the largest absolute value of the eigenvalues. So the norm of the matrix at least tells us, what is the spread of the eigenvalues, right? In what range do the eigenvalues lie? And the inequality says that up to universal constant, this is bounded by square root log of dimension times just the norm of the expectation of x squared. So x is a matrix, x squared is a matrix, right? That's just a square in the sense of matrix multiplication. And now we're taking the expectation inside them, right? So this is a huge difference, right? Here we have the expectation of the largest eigenvalue, but here we have the largest eigenvalue of the expectation. And in particular, this is something that's very easy to compute, right? I mean, it just depends on the data that defines the structure of the matrix. It depends just on the covariance of the entry, right? So if I give you a model of a random matrices, you can compute the right-hand side very easily, right, in terms of the covariance pattern of the entries. And the left-hand side is something very complicated. It's a very nonlinear function of the matrix, right? It tells you something about how large the eigenvalues of the matrix. So this is a very nice inequality. It's nice because it's completely general, right? It doesn't assume anything about the structure of the matrix except that it's Gaussian. And it's easy to apply because the right-hand side is easy to compute. And it's almost sharp in some sense. Why is it almost sharp? It's because we also have a lower bound, which is exactly the same thing except without the square root log. And this is basically Jensen inequality. Because if I have the expectation of a norm, the norm is a convex function, then I can lower bound this by moving the expectation inside them. Actually, this would be exactly Jensen's inequality if I had this. And for Gaussian matrices, there's a classical result about concentration of measure that tells you that the L2 norm and the L1 norm of the matrix is the same. Right? So, so there's a very trivial lower bound, which says that the spread of the spectrum is at least as large as this quantity, which depends only on the variance. And the beauty of this theorem is that it says that this lower bound is always sharp up to a logarithmic factor. So this is a very powerful result because it's easy to apply. And on the one hand, it's very impressive, and on the other hand, it's very embarrassing, right? Because it's very impressive because it makes no real assumptions about the structure of the matrix. But it's very embarrassing because you see, as the dimension of the matrix increases, the upper and the lower bounds get further and further apart, right? So the theorem becomes less and less powerful as you increase the dimension. Whereas classical random matrix theory can tell us exactly what happens as the dimension goes to infinity, right? So in very high dimension, this theorem is not as useful, right? Even though it's just a logarithm. So depending on the application, you may or may not care about that logarithm. But from the point of view of random matrix theory, this is only very crude information, right? It only allows us to pin down the behavior of the matrix up to a factor that diverges as the dimension goes to. So you might think maybe one can improve these inequalities. So in order to show that, let me give you two examples. So the first example of a matrix with jointly Gaussian entries, if I just take a diagonal matrix with IID standard Gaussians on the diagonal and zeros everywhere else, right? This is certainly a matrix with jointly Gaussian entries, right? So what is the expectation of the norm of the matrix? Well, that's just the expected maximum of the diagonal entries, right? Which the maximum of D standard Gaussian variables is of order square root log D. This is a simple union bound. And on the other hand, what's the expectation of x squared? Well, this is obviously the identity matrix, right? Because I just take the square of the diagonal entries. So if we go back to the previous slide, you see the norm of the expectation of x squared is 1, but the norm of the random matrix is the largest eigenvalue is of order square root log D. So that shows that in this setting, this first inequality is sharp. We have to have this square root log D factor there, right? Otherwise, the inequality would be wrong. We cannot just remove this dimensional dependence of the inequality. On the other hand, you know, one could argue that a matrix with diagonal entries is hardly an interesting thing, right? I mean, you don't need random matrix theory to explain the largest eigenvalue of a matrix, a diagonal matrix, right? Because just the maximum of the diagonal entry. So if we look at the classical model of random matrices, this is the simplest model of random matrix theory, so-called Wigner matrix, where all of the entries are independent, are standard Gaussian, let's say. So now all of these are standard Gaussian, and their IID, I made itself a joint, but their IID above the diagonal, and I've rescaled it by square root d exactly so that when we compute the expectation of x squared, we get again the identity. Okay, so that's why I have this scaling. So the expectation of x squared is again the identity. But in this case, this is a classical model of random matrix theory. It's been known for a very long time how it behaves, because here you can let the dimension go to infinity and compute the exact asymptotics. And most of you, or many of you, have probably seen this. If you draw, for example, a histogram of the eigenvalues of this matrix when D is very large, it will look exactly like this beautiful Wigner semicircle distribution. So it lives between -2 and 2. And the histogram of the eigenvalues look exactly like this. It's a perfect semicircle as D goes to infinity. And the largest eigenvalue of the matrix goes to 2, right, which is the edge of the semicircle. So these are results from classical random matrix theory, which are proved by computing the exact asymptotics. And in particular, this means that the expected norm of x is 2 plus little o1, right? And you see in this case, there is no square root log d, right? In this example of classical random matrix theory, this first inequality here is very nonchalant, right? The square root log d shouldn't be there. Actually, it's the lower bound that is already. So these examples show that these inequalities in general are the best you can do, because the expectation of x squared can be the same for two different matrices, and then for one of these matrices, the top inequality is the right gives the right answer, and for the other matrix, the lower inequality gives the right answer. So this shows, we get this very crude information about this matrices, but it doesn't really explain the precise behavior of what is done. These examples show you the level of detail that you can extract from this theory of these type of things. So, I just want to say as an aside, I wrote down inequalities for Gaussian matrices, but these inequalities that are written over here, there has been a lot of work on extending these to non-Gaussian matrices, and this gives rise to a theory, non-Gaussian extensions. This gives rise to a theory called matrix concentration inequalities. And there's a very nice book by Joel Trop that's all about this, that is well known and that you can read. They're called matrix concentration inequalities because the proofs of them somehow mimic the proofs of classical concentration inequalities. And this old result from 1980s about Gaussian matrices is just a special case of these more general non-Gaussian results. And all of these results have somehow similar methods of proof. And in particular, they all have the same drawback that this result has, that at the fundamental level, they behave the same way. There is this square root log d factor that shows up everywhere in these inequalities. And sometimes it's sharp, sometimes it's not sharp, right? So this whole theory allows you to apply the same techniques to much more general matrices which are not Gaussian. But at a fundamental level, the imprecision of these inequalities is exactly the same for all of this whole theory of matrix concentration. So a question that naturally comes up if you see this is, and that is, the most natural question you can ask is, are there more precise inequalities that can do a better job at explaining the behavior of random matrices? Because in practice, you see most random matrices one encounters in practice for which one can do exact computation turn out to behave more like the second example. So this square root log d factor in almost all interesting examples, the diagonal matrices are mostly the exception. For most interesting examples, it turns out this square root log d factor shouldn't be there, and actually the lower bound here gives the right answer. And it's not at all clear from this theorem when that should happen, right? Because you see, you cannot just explain this from the parameter the expectation of x squared, because we have two matrices with the same expectation of x squared that have different behavior, right? So a very natural question you might ask is, can one introduce a different parameter of the random matrix that explains when that factor square root log d shouldn't be there and when that factor square root log d should be, right? And having such a theorem would give you a much more precise tool to study any given random matrix that you encounter in an application. So this is a very basic question. Can we explain when the dimensional factor can be removed? And I and my co-authors and various other people have thought about this question for many years. And we understood the answer to this question in certain special cases. For example, for matrices with independent entries, we have a fairly good understanding of this question developed over many years. And there is a very small number of other cases in which something about this is understood. For general random matrices with dependencies and general structure, in the same setting, for example, as the non-communication inequality, we knew basically nothing. So, it was completely open, this question, to get better inequalities that capture the structure of the matrices. And then very recently, we managed to prove such inequalities. I'm going to show you what they look like. But let me say up front that actually, once we understood how to prove such inequalities, we get an enormously sharper things than we ever expected. So it turns out that our theory doesn't just explain this question. I don't know how to explain this question in another way in this general setting. But once you have the right theory, it turns out it doesn't just explain this question. It gives you a new set of tools that allows you to make very, very precise predictions about almost arbitrary random matrices. And in order to do that, you have to change the perspective on what you're trying to achieve, right? Before I wrote down, let's say, inequalities for the spectral norm of some random matrices. But we're going to have a change in perspective that's going to allow us to answer much more general questions, including, as a special case, to give an answer to this question. So what I want to do in the rest of the talk is I want to give you some sort of high-level idea about how this theory works and what are the objects that appear in it and how to use them in practice. I will not be able to give you very precise definitions of everything, but we try to write the papers in a readable way, and I hope to give you some sort of high-level idea about how things fit together, so you have some intuition about what is going on. So let me start there. So here is the high-level idea about how this theory works. So let's forget for a moment about trying to improve matrix concentration inequalities, which was the question as I phrased it on the previous slide. And let's try more broadly to understand how to understand the spectrum or the eigenvalues of a random. So we start with a given random matrix X. So let's say in the setting that we consider in the non-communication inequality, so let's say it has mean 0 and it has jointly Gaussian entries in itself, right? But no assumptions on the covariance structure. Now, rather than try to bound the eigenvalue, for example, give an upper bound on the norm, we're going to do something completely different. What we're going to do is to each such matrix, we're going to associate some other object called X free. And the way you should think about this X free, right? So this is a random, or let's say, right? So X is a random D by D matrix. But X free is deterministic. Is there a question? Infinite dimensional operator. It's a certain infinite dimensional operator, which you should view as a sort of Platonic ideal associated to this random matrix. So to each random D by D random matrix, we associate a certain deterministic infinite dimensional operator X free. We didn't invent this operator, but I'll tell you a little bit more about it. That we think of as being like the idealized version, the deterministic version of this random, okay? And there is a recipe for taking a given matrix X and spitting out the definition of this object X3, which is a deterministic infinite dimensional operator. Now, this operator X3, it exists, or it comes from the theory of free probability. Free probability, non-commutative probability. And the beauty of it is that we can compute everything about this deterministic object by explicit formula. This theory of free probability provides a sort of calculus for computing exactly the spectrum of X3. So it's a deterministic object. Free probability theory gives you formulas, for example, for the spectral distribution, right? For the histogram of the eigenvalues. Well, it's an infinite dimensional operator, so there's a continuum of eigenvalues, right? But we can compute its spectral distribution explicitly. We can have a formula, an explicit formula for the norm of X3, for example, for the largest eigenvalue, for the smallest eigenvalue, et cetera, et cetera. We have we have explicit formulas and equations that describe the spectrum of X3. So X3 is something that we can compute with, right? It's something we can sit down and do computations, right? And get exact formulas. Now, the reason that in free probability was motivated by the theory of operator algebras, but it's very closely connected to random matrices. We also did not invent the connection between free probability and random matrices. But the reason, the classical connection between free probability and random matrix theory is that the theory of free probability explains that there are certain very special models of random matrices whose spectrum converges to X3 as you take the dimension goes to infinity, right? So it's not as though you can take any random matrix and understand what is going on. No, free probability theory says, okay, given such an X3, we can construct a sequence of random matrices of a special kind whose dimension goes to infinity, such that the eigenvalues converge to this distribution of X. But that doesn't tell us anything about X. So the phenomenon that we discovered is that actually under weak assumption, the spectrum of X already behaves like the spectrum of X3 for any matrix X, right? So here we're not constructing a sequence of special models with dimension goes to infinity that converges to X3. I give you any D by D random matrix X with jointly Gaussian entries. I give you a recipe of constructing the associated operator X3. And what we understood is that there's a parameter that quantifies this, but they're under very mild assumptions. The spectrum of the random matrix X already behaves like the spectrum of its Platonic ideal. And when this is the case, you can use this free probability model to compute all sorts of things that apply to finite dimensional, almost arbitrary finite dimensional random. And this perspective allows us to solve such problems very nicely. So for example, let me give one example of a result. So here is a theorem. So we need some parameter that quantifies, the behavior of the matrix, right? So let me introduce the following object. Cov X is what? Well, X is a D by D matrix. So it has D squared entries, right? So let's take the covariance matrix of the entries of the matrix, right? So this is a D squared by D squared covariance matrix of the entries of X. And then we have an inequality that looks like this. The expected norm of X is bounded. Now there is no universal constant here. It's with constant 1 by the norm of the Platonic ideal, right? So the largest eigenvalue of X is bounded by the largest eigenvalue of this deterministic object, plus a constant times the norm of the covariance matrix of X to the 1/4 times this parameter that shows up in non-communication inequality times here is some logarithmic factor in the dimension. But you see here the logarithmic factor in the dimension shows up in the second term, which in many cases is much smaller than the first term. Okay, so here is a typical example. So what this theorem shows is that the norm of the covariance matrix of X, its size is controlling the degree to which the random matrix X behaves like this Platonic ideal. So let me, let's go back to the question. So we had the original question is, can we explain when the square root log D factor should be removed? So it's not obvious exactly from this theorem, but this theorem really does explain that, right? So here is a fact. If X is a matrix with mean 0, then the norm of x3 is bounded by 2 times the quantity that appears on the right-hand side of the non-commutative Khinchin inequality. Okay. This is a simple computation that you can do if you using tools from free probability theory. Right? And if we take this very simple inequality and we plug it in here, then we get an inequality whose leading term over the leading term, the first term, looks exactly like non-commutative Khinchin, but without the square root log term. Right? Now there is a second term, right? And the second term does have a logarithmic term, but it has a different parameter, the norm of the covariance matrix of X, which may be much, much, much smaller than this parameter, right? And so whenever the second term is negligible, right, the first term dominates, and we can remove the square root log d in the non-commutative Khinchin inequality, right? So the upshot is that we can remove square root log d in the non-commutative Khinchin inequality if the norm of the covariance matrix of X divided by the expectation of X squared is much, much smaller, let's say, than 1 over log d cubed. And this provides, in a sense, an answer to the question. You know, if you think back to the two examples that we studied before, right? We had the diagonal matrix. In the case of the diagonal matrix, you could not remove the log term in non-commutative Khinchin. But in the case of the diagonal matrix, the covariance matrix of the entries were II standard Gaussian, right? IID normal 0, 1. So the norm of the covariance matrix of the entries was 1. The expectation of X squared was also 1. So the left-hand side is 1, which is not much, much smaller than 1 over log 2, right? So the diagonal matrix does not satisfy this condition. Right? But if you think about the Wigner matrix has independent entries of magnitude 1 over square root d, right? So for the Wigner matrix, the classical random matrix with independent entries, the left-hand side here is actually 1 over d. And 1 over d is very much smaller than 1 over log d cubed, right? It's not even close to being on the border where this theorem says that we can understand the matrix through its Platonic idea. Right? So in that case, this condition is very much satisfied. And this theorem explains why, in that case, you can remove the square root log d term in the non-commutative. So this provides an answer to that question, but it's one of the nice things about such a theorem is it's very easy to compute. And that the condition that we have over here actually turns out to happen very easily. In many matrices satisfy this condition. So let me give you a very quick example. So suppose that, suppose that the expectation of X is 0 and that X has independent columns. So X is this matrix, right? It has a column x1, x2, so xd. So the columns are independent. And let's say that the ith column is Gaussian with mean 0 and variance Ci. So the covariance matrix of the ith column is Ci. So you can have dependencies in the column. Now, of course, such a matrix is not self-adjoint, but there's a standard trick you can apply to make this matrix self-adjoint, which is that the norm of a non-self-adjoint matrix is the same as the norm of this matrix where you've multiplied the dimension by 2, right? So this matrix here is self-adjoint, and it still has jointly Gaussian entries. So we can just apply the theory to this matrix over here on the right-hand side. And if you do the computation, it's very easy. You will get an inequality that looks like this. It says the expected norm of this matrix is bounded with constant 1 by the norm of the sum of the covariance matrices plus the maximum of the trace of the covariance matrices plus the lower order term, which is the maximum of the norms of the covariance matrices times log d to, let's say, 3 halves or something like this, roughly speaking. And you see the first term over here, this is the leading term, right? So in non-commutative Khinchin inequality, you would get this leading term with a factor square root log d in front of it, right? But in this inequality, the square root log d only shows up in the last term here. But this last term has a parameter in front of it that is much, much smaller, right? This is the maximum of the largest eigenvalues of the covariance matrices. Whereas in the leading term, you already have the maximum of the sum of the eigenvalues of the covariance matrix, right? So under very, very weak assumptions, there can be situations where this last term is large. For example, when you have diagonal matrices, right? But under very weak assumptions, this last term will be negligible compared to the leading term, right? As long as, let's say, the norms of the covariance matrices are smaller than 1 over log times the trace of the covariance matrices, right? Which is a very mild assumption in most cases, right? This last term will become negligible, and we will get here the exact behavior of these functions. So again, in the case where you have independent entries, not just independent columns, this theorem, we had completely different techniques to study it before, and we got bounds that are very similar, slightly better, but very similar. But already in this case where you have independent columns, but with arbitrary covariance matrices, this was completely out of reach of previous results, right? And now you see it's sort of an effortless computation to get such very concrete and easy to use bounds from the type of theory that is explained by these free probabilities. So, Mariana, how much time do I still have? Do we start? We started a couple of minutes late, but
yes, you have until the seminar ends at 12:30. So if you can take another 20 minutes.
Okay,
probably.
Great. So, so far, I want to give one very quickly. I'm just going to skim over it, one example, and I'll wrap up with something else. So far, I've focused here both in the inequality that I gave and in this, for example, this special case that we demonstrated. I focused on inequalities that look very much like the matrix concentration inequality, right? It's the expected norm of X is upper bounded by something that you can compute directly from the model. Right? But one of the nice things about this theory that we developed is that we have access to much, much sharper information. For example, this leading term is just an upper bound of the norm of X3, but the norm of X3, you can compute it actually explicitly. And you might wonder, that, okay, that sounds great, but in let's say if you're doing an application to data science or something like that, right, or whatever people are interested in this seminar, do you really care about having something that sharp? I mean, in such applications, maybe you wouldn't care about the constant. You could have it up to universal constant. Maybe you wouldn't even care about the square root log d and not the unit inch, right? Because it's used very often. And I want to try to convince you that when you have this very sharp theory, you have access to answering questions that would be completely outside the reach of classical inequality. Okay? But you have to change the way that you think about this problem. And to do that, I just very quickly want to give you another example. Actually, the example I will give is a very classical example, but it was studied in classical random matrix theory using specific tools. And I want to convince you that using this kind of theory, you have access to answering such questions in a much more general sense. So let's consider the following model. So now I'm going to take a model with non-zero mean. Actually, the inequality I wrote here, unlike the non-commutation inequality, works even when you have non-zero mean. So we can look at the norm of random or the eigenvalues of random matrices with arbitrary. So let's exploit this. And let's look at the following classical model. It's called a spiked covariance matrix model. So we take a rank 1 matrix, let's say without loss of generality in this example. So theta is some constant more than 0. E1 is the first coordinate vector. This is a rank 1 matrix plus a Wigner matrix. So a matrix with ID. This model is called a spiked covariance matrix. Right? So the idea is that, here's the intuition. Right? If we just had this part, if theta was 0, right, then the spectrum of this from classical random matrix theory, the asymptotics of the spectrum would be this semicircle. But now we added a rank 1 perturbation to this of string theta, right? So you might expect that maybe there is one extra eigenvalue, let's say at theta or something like this, that you can see in this picture, right? So it turns out that exactly what happens is that when theta is small, the spectrum of this matrix looks basically exactly the same as -2, 2, right? This extra eigenvalue is hidden here inside the bulk of the spectrum. But when theta is sufficiently large, one eigenvalue pops out and you get this outlier. And the phase transition was computed exactly by Baik, Benarous, and Péchet. It's called the BBP transition. it turns out that you get this spike at theta plus 1 over theta, as long as theta is more than 1. And then when theta is less than 1, there is no outlier eigenvalue. All of the eigenvalues. And this phenomenon, yeah, it's called the BBP transition. It was computed using classical random matrix theory. And it is used a lot, for example, in data science to understand, limits of detection and things like that. So I want to try to convince you that, well, I'll just hand wave it, right? So I claim that this phenomenon follows just as a simple computation from our results, right? What should we do? Well, actually, right, let's not look at the random matrix itself. Let's look at the associated X-free. So remember, to this random matrix is associated a free model, right? So if they have an outlier here, we should be able to compute it by looking at X-free. So how do we compute the largest eigenvalue of X-free? Well, there's a theorem due to Lehner which gives us a formula for it. So for example, the largest eigenvalue of X-free, it's equal to the infimum over all positive definite matrices of the largest eigenvalue of this strange looking matrix. There it is. It's some sort of variational formula, right? But it's a variational formula that involves only the mean and the covariance matrix of X. So in principle, it's something that you can easily compute, or easily, maybe not easily, but it's something that depends only on this on the input of the the data that defines the matrix. And in principle, you should be able to compute this, and you will have the exact edge of the spectrum of this Platonic ideal, right? And in this case, the norm of the covariance matrix of X is much, much smaller than the expectation of X squared. It's of order 1 over square root D. So our theory kicks in, and our theory says that if you compute the X-free as the largest eigenvalue of X will be very close to this quantity over here. And then all that's left to do is to compute it. And in this example, this lambda max of X-free, it's like a 3-line computation to show that it's 2 if theta is less than 1, and 1 over theta plus theta when theta is more than 1. There we go. And we recover exactly this transition behavior. But you see, it follows just as a very special case of a general theory. And once you understand that the random matrix behaves like this deterministic counterpart, understanding a phenomenon like this just becomes a deterministic computation. And the computation may be easy or hard depending on how complicated the model is. But you now have you can now turn answering such questions essentially into a recipe that you have. Right? It takes the randomness of the random matrix out of the picture. And in principle, one should be able to answer these questions for much more general models. But of course, the free probability computations will become much harder if you have complicated models. But nonetheless, you get the idea of things you can do with these type of theorems that would be out of the question. You would never see such a phase transition behavior from using estimates from matrix concentration equalities. Would be completely out of the question. So let me wrap up with just a couple of remarks. So I focused on the extreme eigenvalues, the norm, in this talk, mostly because that's what classical matrix concentration equalities give us, and I wanted to compare to that. But in fact, our theory allows us to compute things that are normal to compute in classical random matrix theory, but that in this theory of sort of generally structured random matrices were so far completely out of the question. Right? So just some sort of, vague overview, right, of what our results say. Our results say that there is this parameter, right, if it's sufficiently small, but only logarithmically small, right, then X and X-free, this deterministic model, have very similar behavior. But it turns out it's not just in the sense of norm, right? What we know is that the spectral distribution of X is very close to the spectral distribution of X-free. So not just can we say something about the extreme eigenvalues, we can draw pictures like, you remember like the semicircle. If we draw the, what I said is if you draw the histogram of the eigenvalues of this Wigner matrix, you get something that looks like a semicircle, right? We can do exactly the same thing for arbitrary structured matrices. And if you draw a histogram of their eigenvalues, the theory says that under this very mild condition, the histogram of the eigenvalues will be very close to the histogram of the eigenvalues of X3. Now, the histogram of the eigenvalues of X3 is very strange. It doesn't have to look like a semicircle. In general, it looks like this. It's a bunch of these strange blobs. Here is an example of what the spectral distribution of X3 might look like in some example. So it can be complicated, but it can be computed explicitly. There are explicit formulas that allow you to compute what these densities look like. Okay, so they might not be pretty, but they look good, right? And our theory says that under this very mild, very easily computable condition, if I draw the histogram of the eigenvalues of the given random matrix X, it'll look exactly like the strange picture. Now, similarly, when I said that the largest eigenvalues of X are close to X3, I just meant that the largest eigenvalue of X is close to here and the largest eigenvalue of X is close to here. So you cannot have eigenvalues here, right, or here. Right? But our theory also says that you cannot have eigenvalues over here in these gaps. No eigenvalues in the gaps. So in the limit, all of the eigenvalues has to lie where the X3 has eigenvalues. Third, rather remarkably, we can say the same about polynomials of such random matrices. So if you take, let's say I take several such random matrices with jointly Gaussian entries and, arbitrary structure, and I take some polynomial of them, x, y, x squared, z to the fifth, y, x, y, x, y, right? Let's say that's a polynomial, plus z squared times yx, right? Here's a polynomial. Then our theory will still say that if these matrices satisfy this condition, then that polynomial will have the same spectrum almost as the polynomial of the free guys. And again, those things can be computed, right? So those are nonlinear models of random matrices that can be accessed in the same way. And the fourth thing is that all of this is non-asymptotic. So everything is expressed in terms of explicit estimates of how close these things are in terms of these parameters, the norm, the covariance of X, right? Which means that you can very easily use these type of conclusions as input to other analysis of things you might be interested in, right? It's not asymptotic results are often difficult to use as input, but when you have explicit inequalities, you can just use this as input to other analysis and you get a powerful. And at the very last 30 seconds, I just want to say that I focused on Gaussian matrices, but just like matrix theory of matrix concentration equality gives you very broad extension to non-Gaussian matrices, we can have exactly the same type of extensions here. That turns out to be a completely separate story. So to the non-Gaussian case, we do this by a separate principle, a universality principle, which with my PhD student, Tatiana Brailovskaya, I forgot to say that all of the previous work that I mentioned was joint work with Afonso, Bandeira, and Boedihardjo. So there's one paper where we work out the Gaussian theory, and we have a second paper with Tatiana where we work out the non-Gaussian theory. But basically what we show is under some very mild conditions, the non-Gaussian matrices behave like the Gaussian matrices. And then you get you automatically get an extension of all of this theory to the same kind of models that can be treated by matrix concentration. So we really get a very sharp theory that explains all of these phenomena. So let me end there. Thank you very much.
Well, thank you very much. Let's all thank our speaker. And I guess we can open the Zoom for questions. Anybody?
So Ramon, I have a question. This is Venkat Anantharam from Berkeley.
Hi.
Hi, I have a question about your condition. Actually, it happens to be on the slide. So if you look at the case where the covariance matrix of X is kind of small, like you have, isn't that saying that it's X somehow, the entries of X are somehow far from being IID in some sense? So there's matrices are somehow have the entries that are quite dependent?
No, it's the opposite, I would say. You see, it's the ratio that you want to be small. Right?
No, but you have the individual variances of the entries also showing up inside your covariance matrix, right?
So the IID case is the best case. In the IID case, this is 1 over D. So if you have IID entries, the left-hand side here is 1 over D. And I believe you can't do really any better than that. So this is the best case situation, right? The beauty of these results is that you have 1 over log D on this side. So you can be very, very, very far from being IID and still satisfy this condition. For example, let me just, even if you have independent coordinates, let's say you had a very, very, very sparse matrix where it's a D by D matrix, but in every row you have only, let's say, log D to the 4th non-zero entries. And those entries were, let's say, IID. Then you would be near the boundary of where this was.
Okay, so yeah, I get it. So your covariance matrix is a D squared by D squared matrix, which would be diagonal in that case.
Right.
Okay. I guess I just had my normalization.
Exactly. So if you have independent entries, the covariance matrix is diagonal, right? And it has the magnitude, right? But the norm of the expectation of x squared can also be expressed as the covariance matrix of x, right? But now you take a sum over the rows, right? Because what is the covariance matrix of x? Maybe it will just clarify to write down the formula, right? Maybe I think this will clarify this.
No, I mean, I've already figured it out, but you're welcome.
Okay. But let me just, because you asked, right? The covariance matrix of x, ijkl, right? This is the expectation. Let's say it has mean 0, right? It's this, right? If it's mean 0 and real, right? But the expectation of x squared is the sum over j of the expectation of you know, the xij, expectation xij, xkl, right? IL, and then here we should have a j, right? So it's like you're taking a sum of many entries of the covariance matrix, right? It's the sum over j of the covariance matrix xij, lj, right? And so roughly speaking, what we need for this to set in is that this guy is much, much smaller than this sum divided by square root log d. But this is a sum of d things. So that's a very weak assumption, right? It's violated if you have diagonal matrices, right? Where every row has only one non-zero entry. But if you just look at the formulas, right? We just want to show, roughly speaking, that, I mean, I'm hand waving a little bit because these are spectral norms, but roughly speaking, that you want to show that each individual covariance is smaller than their sum, smaller than square root 1 over square root log d, or 1 over log d cubed times the sum. Yeah. And so this doesn't require version.
So the basic, at least in the context of the presentation today, the basic parameter that controls the ensemble is just this covariance matrix, right? The covariance matrix of X. I mean, you've been talking about the jointly Gaussian case.
Yes.
So it just boils down and everything means zeros and it's self-adjoint. So basically the covariance matrix of X is somehow the parameter that controls things. So would it be possible to describe what your X-free object is as a function of that covariance matrix?
Yes. So I can describe it to you, but it requires, I'll write down exactly what it is. But and this is also true, by the way, in the non-Gaussian case. So what happens in the non-Gaussian case is there's just a separate parameter that controls how far you are from being Gaussian, right? It doesn't interfere with the Gaussian field, right? So what is X-free, right? So X, right, it has entries, X11, X12, etc., right? And they're jointly Gaussian with some mean and covariance. And X-free is the same thing, right? So this is still a D by D matrix, but you replace each entry by an operator where the entries are a semicircular system with the same mean and covariance as X, as the entries of X. So a semicircular system is like a non-commutative analog of a Gaussian. These are some sort of infinite dimensional operators that behave like non-commutative Gaussians. They're like Gaussians, but they don't commute with each other. And so basically what you do is you just take this D by D matrix X, and you keep the same mean in the covariance, but you replace all of the Gaussians by non-commutative form of analogs of these Gaussians. Okay. And that's the model. So it's something that if you understand what this word means, is a very simple and clean object.
I have some sense of it. Yeah, I'm not sure I understand it, but okay. All right, thank you.
I mean, it's something one has to sit down and just look at the definition, right? I mean, it's not that hard in a sense, right? You have to know what it is, right? So X is a random matrix, right? Let's say with complex values, And this X3 is a D by D matrix, but it lives in the set of operators, C-star algebra of these operators.
Thank you.
So I also have a question. In the very recent paper with Brailovskaya, and also in today, I believe, you mentioned that the covariance essentially measures the distance to the free version.
Yes.
In some sense.
Mm-hmm.
But I do not really see why that should be true, because the free version is also constructed using the covariance.
It's completely not obvious.
Hmm?
It's completely not obvious. And, you know, I have to apologize. You know, I in this talk, I really told you very little about the mathematical intuition and ideas behind these results. And, you know, I can only say so much in the time, and I thought that for this audience, it might be more useful to understand how to use the results than for me to give you some philosophical discourse about mathematics. But yes, it should not be obvious to you why the norm of the covariance matrix of the entries of X has anything whatsoever to do with the behavior of these random matrices and their free complement. And that's something that comes out of the theory through several steps. There's two things one has to understand to get there. The first thing you have to understand to get there is that, you know, what have we done? The relation between X3 and X is that we replaced the entries by non-commuting entries, right? Non-commuting analogs of the entries. So it does make sense in some sense that X will behave like X3 if X itself was already sufficiently non-commutative. Right? Because if X is already sufficiently non-commutative, then you're not changing much by making the entries of X non-commutative. And there is a certain quantity that measures this. I mean, if I take two IID copies of X, right, you could look at the expectation of X, X prime, X, X prime. Let's say the norm of this, right? So if X and X prime, if X was very, let's say in the diagonal case, if I take two IID copies of X, they commute with each other. Right? So then this would be the same as the expectation of X squared times X prime squared, right? In the commutative case. Right? So if this is much less than that, then you are very non-commutative. And you can imagine that if you're very non-commutative in that sense, that then maybe you could model X well by something that's very non-commutative. So that's the first step that you have to understand. That's something like this. And the second step you have to understand is that if the norm of the covariance matrix is very small, then you are in this situation. And that these are non-trivial steps. These are non-trivial ideas. And there is a history also of such ideas, you know, that is in the literature, and you know, they were explained in the first paper where these ideas come from.
Okay.
And what they do. So, but no, this should not be obvious to you from my talk, and it's hard to explain that exactly without explaining more about what these objects mean and how they.
Maybe a short question. So in today's talk, and I think also in the paper, the most recent paper, you focus on self-adjoints, as most people do. Am I correct in the assessment that such results are just not currently possible for non-self-adjoint matrices?
For self, it depends on what you want to say for non-self-adjoint matrices. If you're interested in the singular values,
yes, then the trick.
By this doubling trick. If you're interested in the eigenvalues, then currently we do not know how to do that. I don't think it's out of the question that it's possible to do that.
Mm-hmm.
But
okay.
There are certainly difficulties along.
Yeah, okay. Yeah, thank you.
If we wanted to study such a thing, certainly the way we do the theory provides a starting point for doing that. It's not as though that is completely out of the question or one has to discover completely new tools. That's not true at all. So I mean, the theory that we have provides some sort of starting point for answering such questions, but there are, you know, there are difficulties to that.
Mm-hmm.
I would be more motivated to work on this if I had a good example of an application where this was interesting.
Yes.
Okay. Thank you, everybody. Are there any other questions for now? Otherwise, I'm going to turn off the recording. and end the stream, and you're welcome to hang out and keep on asking Ramon any other questions. So I'll stop that. And feel free to
Thank you.
stay a little bit longer. Thank you, everybody. Thank you, Ramon.
I can stay for about 5 minutes, but then I have a next meeting. So this is our first week of class, so it's a little first day of class of the semester. So it's a little hectic.
Maybe a couple of small questions.
Sure.
Did you get a lower bound as well? I guess you do, because at the end you've got this nice concentration of the whole spectrum. So what extent that's tight, that bound, if you see it, it's obviously a lot better than what was there before.
Yeah. It's a very good question. Yes, but the lower bounds are a little bit harder to use right now than the upper bounds, and this is something that we are working